Good morning to everyone, and welcome to the ISGAN Virtual Learning webinar of today, titled Optimal Bidding and Operation of Dynamic Virtual Power Plants Under Uncertainties. This webinar is hosted by ISGAN, and it is in collaboration with the Positive Project. So, now before we proceed with our speakers, allow me to introduce you to ISGAN, which is hosting this webinar. ISGAN is the short name for the International Smart Grid Action Network, a technology collaboration program of the International Energy Agency. ISGAN is also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN creates a strategy platform to support high-level government attention and action for the accelerated development and deployment of smarter and cleaner electricity grids around the world. ISGAN consists of 27 contracting parties. Their nominated representatives form the executive committee headed by the Presidium, assisted by 2 co-secretariats. ISGAN's vision is to accelerate progress in key aspects of smart grid policy, technology, and investment through the voluntary participation by governments in projects and programs. ISGAN activities focus on 5 principal areas: policy standards and regulation, finance and business models, technology system development, workforce skills and knowledge, users and consumer engagement. ISGAN facilitates the dynamic knowledge sharing, technical assistance, peer review, and project coordination among its contracting parties. The ISGAN value proposition relies on conferences and workshops, policy and technology briefs, discussion and technical papers, casebooks, and webinars, like this one. Within ISGAN, virtual learning offers the ISGAN community means of rational and continuous technical skills update in the field of smart grids. The virtual learning is proposed as a set of e-learning and reading core modules dealing with the entire value chain of smart grids. The webinar of today, Optimal Bidding and Operation of Dynamic Virtual Power Plants Under Uncertainty, is organized in cooperation with the Positive Project. In this webinar, the speakers will present the recent result on the optimal bidding and operation of dynamic power plants, considering different types of uncertainties. Energy and ancillary service market participation is defined by means of a novel, robust optimization algorithm. Energy and service provision are then guaranteed close to real time through a continuous optimal redispatch tool. More information on this tool and on the advancements on the Positive Project are available in their website. But today, our speakers will present the details on this novel robust optimization algorithm that has been developed. Our speakers are Lukas Sigrist, Research Associate Professor from Comillas Pontifical University, Álvaro Ortega, Associate Professor from Comillas Pontifical University, and Oluwaseun Enoch Oladimeji, Senior Engineer at EirGrid. Please use the question and answer tool to pose your questions. The speakers will be happy to answer to your answers and to your questions at the end of the presentation. All the recordings will be available in the ISGAN YouTube channel. So now I can leave the floor to Lukas.
Thank you, Matteo. Thanks a lot for the introduction. And first of all, thanks a lot for the opportunity to present our progress and our work we carried out within the Positive Project. The agenda today is I will give a short introduction, let's say the context of the whole project. And then I will hand over to my colleagues, to Álvaro and to Enoch, who will talk about the optimal bidding of the dynamic virtual power plants and then the real-time operation of dynamic virtual power plants. And then we just wrap up with some conclusions and hand over to the question and answer part. So what's the context of that webinar and the whole work we are presenting today? So the work has been carried out within a European project called Positive, which stands for Powering System Flexibility Through Dynamic Virtual Power Plants. The main goal was actually to facilitate through this dynamic virtual power plants the integration of renewable energy sources in the power systems. You will see that dynamic virtual power plant is kind of a virtual power plant. That's why it's within the name, but it includes further aspects which have not been actually dealt with till this project. Within the project, we have a couple of other partners, of course, many from Spain, some from France, from Germany, and from Switzerland. The leader of the project coordinator, comes from École Centrale de Nantes, and is Bogdan Marinescu. You reduce that, yeah. Okay. So in this webinar, what we going to present is how we can actually configure and operate such a virtual power plant or dynamic virtual power plant optimally. Configuration means what generator or demand assets should be included within such a DVPP, and operation relates how do we plan the operation of the DVPP and how do we handle real-time disturbances. The important thing is that the DVPP we consider only consists of renewable energy resources and flexible loads. So we do not consider conventional power plants, and we don't want to consider electrochemical energy storage systems. So we exclude them explicitly. We try to answer within that project, but also today, a couple of questions which are mainly related to how we can maximize the economic benefits of a DVPP, both trading in energy and electric energy markets and in ancillary service markets. And another question is related to the uncertainties within the problem itself. So how can we adapt to them? How can we foresee them and include them in the trading? And how can we actually handle them in real time when they actually occur? Why the focus on renewable energy resources? Well, this is within the whole idea of the energy transition, because they're actually cheap and they're clean, but they have an associated problem. At least some of them, they are non-dispatchable. Usually they're small, at least at their individual individual capacities. And then this non-dispatchability, the inherent uncertainty, well, this leads to some disadvantages. They're exposed to penalties if they're not delivering what they're supposed to deliver according to the market offers. There are some barriers, usually in terms of size, to enter certain markets, and so on and so forth. So the whole project actually tries to foster the penetration. One way is, of course, to include a battery, because, well, the battery can, let's say, mitigate the uncertainties, the variations, but this doesn't come for free. So the battery, well, it is cheap. It can charge and discharge pretty fastly, usually a moderate in size, but their costs are still relatively high. So you have to account their costs if you want to consider these technologies. They have also certain problems with the raw materials, with the recycling, and so on and so forth. So the whole idea is to make use of the existing assets and to minimize, if possible, reduce to zero the need for any additional assets like batteries. So how do we do that? Well, one option is to create this dynamic virtual power plant, which basically is to make use of the unity where we have strength in unity. So we try to combine independent resources and to make them work as a single unit. So we become, a lot of small fishes become maybe one big fish that can participate in the market within, let's see this picture in the sea, and is an important agent. The good thing is, if the resources are of different nature, the better, because they can complement each other. We have a portfolio effect. If they are dispatchable, because some are, like hydropower or biomass power, even better yet. And of course, if we can, and that's what we did, even make use of flexible demand, well, we have an additional asset here. So the dynamic virtual power plant we consider basically consists of non-dispatchable renewable resources like wind and solar PV, but also dispatchable renewable resources, as I said, biomass or solar thermal power or hydropower. All this together we combine within what we call the dynamic virtual power plant. As I said, the whole project addresses the part on the dynamics in a holistic way. So we check and elaborate controls at the individual asset level, at the VPP levels to provide ancillary service, but also we include them within, let's say, the operation of the virtual power plant. The important thing is we do not consider batteries. That was kind of a boundary condition of the whole project. So when we talk about the electric energy markets and how we can maximize the benefits, the good thing is the renewables are cheap. The bad thing is they're usually stochastic in nature, so it's hard to control them, and they're also small in size, so that makes them less competitive. Furthermore, different countries have different market regulations with different market structures. Álvaro will talk more about this. So the sequence of markets, what are the requirements of that markets, the penalties if you do not fulfill your obligations, and so on and so forth. This needs to be handled and considered by the VPP if we want to maximize its benefit. If the DVPP is small, whatever this means, but relatively small, we can use a price taker approach. So that means that we do not influence the market price by making our offers. Of course, the larger that becomes the DVPP, well, the larger its benefits, but also the higher impact actually on the market price. And if you become very big, well, then the price taker approach is not very useful anymore, and you have to use what we call a price maker approach. But there you need to know what the remaining market agents are actually doing. Okay. We will start, you will see, with a price taker approach. And another problem that we need to consider is the uncertainties. So if you are making plans for the next 24 hours bidding, you have to consider that, well, the availability of a resource, for example, wind or PV is unknown, is uncertain. The same for the price. You don't really know what are the prices in the price taker approach for the 24 coming hours. You have estimates, but you cannot be fully sure. But not only we want to participate in energy markets, but also in the ancillary service markets. That we can do because we consider these dynamic aspects, this controllability of the whole virtual power plants, making dynamic virtual power plant. But here the problem is that usually you have some requirements with respect to minimum capacity to enter ancillary services. The individual assets of a DVPP are usually below such capacities, but you can aggregate them and then you can actually become a provider of such a service. Again, the uncertainty here needs to be considered, both in the planning, but also then we see that in the second part presented by Enoch, in the real-time operation, because the variation, the disturbances can compromise the provision of the committed service. And some ancillary services are extremely important, and you cannot allow that you do not provide this service. So the question is, well, how do we handle the uncertainties? How can we anticipate them? So we consider the uncertainty directly in the trading part. So that's the first part of the webinar today. But we also try to adapt to the uncertainties, but rather than said to the events, the disturbances in real time. So in this part, we have to look at much shorter time frames. We do not look anymore at 24 hours ahead, but only a couple of minutes at most ahead, just to guarantee that if disturbances appear, for instance, the wind we expected is actually below, that we guarantee the provision of the energy and the ancillary services. In this regard, the DVPP needs to respond to changes in power set points. That could be, for instance, a control problem like in the AGC, in the secondary frequency control, where a centralized regulator sends new additional power set points to the DVPP, which you need to be able to follow. You need also to respond to possible contingencies within your DVPP. So if one of your units trip, how do you respond? And of course, as I mentioned in the example, you have forecast errors. So the uncertainties realize and you need to deal with them in real time. With this, I hand over to Álvaro. I hope you will enjoy. Thanks a lot.
Well, good morning, everyone. And thank you, Lukas, for your introduction. So, okay, let's try to answer the first two of the questions that Lukas has posed, which basically imply that we will try to maximize the benefits, or we try to minimize on costs, or we try to obtain the maximum benefit as we can by participating in different electricity markets and ancillary service markets as a DVPP, so as a aggregation of units of a particular nature. For that, the first thing that we always need to do is basically to define which business model we want to be followed by the DVPP. In this case, we can identify, for instance, the maximization of the energy market profit, assuming that we only participate in such markets. We can also try to maximize the benefit of participating in ancillary service markets. If we have some flexible demands in our portfolio, we can also try to maximize what is called demand utility, so how well we use that demand. We can also try to minimize some other quantities, like, for instance, the cost, of course. Assuming that we have a mix of generation and demand in our portfolio, then we can try to be self-sufficient, so to try to minimize the amount of energy that we buy from the grid. Basically, we need to identify this business model, but it doesn't need to be one alone. So we can actually make a combination of several of them, as we will see, where we put our focus on maximizing energy market profits, ancillary market profits, while minimizing operation costs. Once this business model has been defined, then the next thing that we need to do very carefully is to characterize the electricity market in which we are participating. For that, we need to understand the sequence of markets that we have in that particular country or system. We have here, for instance, the case of Spain, where we have several markets. So we have the day-ahead market, which is the most common one and the one with the highest liquidity, which covers the 24 hours of the day of operation on the right. Let me just use the pointer. Okay, so we have the gate closer here at 12 hours before the first delivery period for the day-ahead market. Then we have secondary reserve. Then we have several intraday markets that cover different windows. These intraday markets are very useful for us, as we will see, not in this presentation, but if you follow the documentation that we have in our website, in the Positive website, we'll see that in these intraday markets, provided that we have them in that particular system, are very, very useful because they allow us to adjust the schedules that we did for the day-ahead market, because we can assume that we have more accurate forecasts of the uncertainty parameters, prices, and energy production, for instance, because we are closer to the day of to the first delivery period. Okay, so once we have identified that sequence of markets, we need to also know very well what is the payment mechanism for each market. So, for instance, for the secondary reserve in Europe, we can find that some markets do not pay for that at all, or they have some kind of you're obliged to do that, and then others just pay you for the amount that you reserve for that service. Others, they also pay you for the activation, so for the actual delivery of that power. So you need to know how that service is paid in order to formulate your problem. And finally, but not less important, we need to understand very well the interactions between markets. So let's look carefully at what we have here. For instance, so we have a day-ahead market that closes 12 hours before the first delivery period. But we have also here the secondary reserve that is also covering the full day several hours later. But one thing that we can do, and we do ourselves, is to optimize both of them together simultaneously. So we have the day-ahead and secondary reserve market optimized together. Why? Because if we want to have some secondary reserve booked for that service, we cannot use it to be sold or bought in the day-ahead market. We need to have them in separate buckets, if you know what I mean. So we optimize them together. Fine. The good thing is that we can only submit our offer, our bid for the day-ahead market alone. We can still wait to submit the bid for the second reserve, and look at what happens. We have here, very close to this gate, the intraday market one, which also covers the first all the time window. So what we do is to solve another optimization problem where we solve both of the secondary reserve and first intraday together. So basically, what we booked for the secondary reserve, since we haven't submitted that bid yet, we can move it, shift it into the first intraday market if we see that we can get more benefits by doing so. Okay, so we need to understand very carefully, very well, all these features of the market that you're participating in. The next thing that we need to do is to identify very well the input data that we need to formulate our problem. Thankfully, most of the data that we need, it's time independent, meaning that is fixed, that is the same for all time periods. Think, for instance, the capacities of the units that compose our DVPP portfolio, the ramp limits, or the costs, operation and maintenance costs, all of that, once it's defined, it's fixed. We don't need to touch it. However, there are other parameters that are uncertain, and we need to provide some forecasts of them for each time period. Of course, clear examples are the different market prices, the available power production of stochastic sources, wind, solar, and of course the hourly consumption of demands of the flexible demands that we can have in our DVPP. So to deal with these uncertainties, we are using in Positive what is called robust optimization, where in order to do that, we are going to talk about that more in detail later. But here, what we need to define, it's the input that we need for that robust optimization. And for that, we need the probabilistic density functions of the distributions of that uncertainty. So for each time period, we have here a figure on the right of the forecast of the solar irradiation in a solar thermal unit for different hours in a particular day. And we can see that, first of all, they are not symmetric, and they are far from symmetric, actually, and that they vary substantially from time to time. So we need to be careful. We need to have some sort of forecasting tool that gives us this kind of information. But then the good thing is that for the optimization problem itself, we need to pass only the median of this distribution, so the value for which 50% of the values are lower than that and 50% higher, and the maximum and minimum deviations. So only the median and the maximum and minimum deviations. We only need that for the optimization problem, okay? Once we have that, we can define our problem formulation, okay? So some of you might be familiar with this type of notation in optimization problems. For those who are not, don't worry, because the scope of this webinar is not to dwell too much into the mathematics, but it's just to give you a glance of how the problem transforms from a deterministic problem, so a problem where we know exactly all the parameters, to a problem where we have some uncertainties, okay? So if we start from a deterministic optimization problem, where we have a maximization in our objective function with some constraints, equality and inequalities, to move into robust formulation, what we need to do is to first identify what is the uncertain parameter. In this case, it can be this cost or this price, for instance. And in this case, we define it as the median that we mentioned before. So we have here the most expected value for our uncertain parameter. And then the robust formulation, what it does is to optimize the worst realization of the uncertain parameters. So if you look again, for instance, here, even if we have this distribution as we are passing the median and the minimum and maximum distributions, what is taken is the optimal solution for the worst realization. So if imagine, for instance, that we are a net seller, so we are generating unit like the solar thermal unit here. If we define the median, say for instance 150 for hour 10, the worst realization it's going to be which one? 50, because whatever happens, the worst condition for us is to sell less power than we expected. And we do that for every hour and for every uncertainty, okay? So that's what the robust formulation does. And the main problem with that is that it can be too conservative. I mean, it's easy to formulate, and it's easy also to parameterize because we just need to pass 3 data for each uncertain parameter. But the main problem is that it can be too conservative. It's basically for every hour, your forecast, it's always really bad and it goes into the worst condition. So in order to relax that constraint, what we do is to include what we call robust uncertainty budget, which is this gamma over here. And with that, which is a user-defined parameter, what we can do is to define how good our forecast is. So basically, we are defining how much do we trust that forecast. So if we think that our forecast is very good, so that is going to be very, very close to what we expected as median, then we can define this value close to 0. If we think that our forecast is very bad, then we can define this parameter with a high number. How big? Well, if we have 24 periods in the day-ahead market, for instance, then this can be close to 24 or equal to 24. And with that, we define how much we are subtracting as the worst realization to the expected incomes in this case. So we can define the level of conservatism of our program. Now, this is the formulation for when the uncertainties are in the objective function. Now, we can write a similar problem when the uncertainties are in the constraints. So let's take, for instance, the simple example of a stochastic source, the power production of a stochastic source, which is delimited by the maximum power production available at each time period. Now, this is, of course, for stochastic sources, uncertain, and therefore we define it with the median of the distribution. And then we write a similar set of constraints, okay? They are a little bit more involved, but it's a similar set of constraints for that. We can, I can give more details of that after the presentation if needed. And again, we can define another robust uncertainty budget for each uncertainty in the constraints, which cover again from 0 for forecast that we trust a lot to 24 for forecast that we don't trust at all. And that's it. So we need to define this for every parameter, okay? So sorry about the formulation, but I think it's needed to understand at least conceptually what is going on with the robust formulation. Let's try to see it visually what is going on, okay? So here we have, as an illustrative example, a case where we have a non-dispatchable unit, take for instance a solar PV plant, trying to sell some power to the day-ahead market, okay? So what do we have to define as uncertainties? Well, the price of the day-ahead market, where we have a solid line, the median, and then some upper and lower bounds of the distributions. And we do something similar for the non-dispatchable unit. We have the median, so the expected energy production, and the lower bound. Why don't we consider here the upper bound? Well, because as I said before, the worst condition is always going to be to have less power than expected. Whereas for the price, we don't know a priori, because we don't know if we are going to be a seller or a buyer for every particular period. So we need to consider both up and down, and for most of the time, it's going to be asymmetric. But for the non-dispatchable units, for instance, this is simplified quite a bit. If you had, instead of a generation source, you have a demand, then you're going to have the upper bound of the distribution. Now, let's see what happens when we define these uncertainty budgets equal to 2. So that means that for the period of 5 hours that we have, we are going to choose the 2 hours for which the objective function is affected the most negatively. So the 2 hours that reduces the most our objective function, and then we are going to optimize that, such that whatever happens is going to be better than that, hopefully. So how do we define those periods for instance, for the non-dispatchable unit? Okay, we have 2 approaches. The simplest one is to say, well, I will just take the hours for which I have the highest deviations between the median and the lower bounds, which are these 2. And then the price, which is in the objective function, is going to be choose the 2 hours for which the multiplication of the final price times the final energy reduces the most our objective function, which are these two. Okay, and this is how it's done, and we optimize that set of data. Okay, now, although it's very simple to implement this, it might not be the most accurate representation of what is happening in reality, because in reality, the worst condition for that is not just taking the highest deviation, because you need to take into account also the price at that period simultaneously. You need to solve simultaneously basically a nonlinear problem where you are multiplying price and energy. We call that incomes robustness. And for that, typically what people do in the literature is to solve a multi-level problem, 2-3-level problem. In our case, we are working on a beta version, let me define it that way, such that we are solving that in a single level problem. And with that, we can define the periods of hours that simultaneously affects the most our objective function, and we optimize that. And as you can see, the total profit is lower because we have found the hours that are actually reducing the most that objective function, and we are optimizing that. Okay? Right. So enough with the formulation and the illustrations, and let's see in just a couple of minutes, because I don't want to extend myself too much, some examples of this applied to, again, a DVPP in the Spanish grid. So we are following the Spanish market rules. Our DVPP is composed by several units, so it's heterogeneous. We have some dispatchable units, hydro plant, biomass, non-dispatchable units with farm, solar PV, and 2 solar PVs, 1 solar thermal unit over here, 3 flexible demands, okay? And we try to see what happens when we try to participate simultaneously in the day-ahead and the secondary reserve markets. And we obtain something similar to this, okay? So in the lines, we have the price. So the solid line is the median of the price of the day-ahead market, upper and lower bounds of that price. And then for each period, we have 3 bars that represent the traded energy as a DVPP as a whole, so the aggregated power, for 3 cases according to the values of the uncertainty budget. Optimistic, so we assume that our uncertainties are equal to the median, so it's a deterministic problem, let's say. A balanced condition, so our forecasts are not accurate, but not so bad. And then pessimistic, where we assume that our forecasts are actually very bad. And we can see that the trend is that we sell less and less power, the more conservative our strategy is, becoming energy sellers in some periods that we are clearly energy buyers in periods where we are clearly sellers. So we have to carefully define, it's a very sensitive parameter that we need to define, okay? And this is for the day-ahead market. We can have similar information on the secondary reserve. So this is, for instance, for the balance condition. And this is the traded energy. And here we have the power that we reserve for the secondary reserve market. And the thing is that the more conservative our strategy is, we have observed that the more we want to keep some energy, some power for the secondary reserve and less for the day-ahead market. So we kind of try to be to move that energy that we don't know that we are going to have to the secondary market. Why? Because then later on, we can try to adjust it better in the first intraday market, as I explained you before. And with our formulation, we can see also what is going on with each of the generating units, for instance. So the more conservative our strategy is, we can see how the available energy of each unit is reduced. So we can identify which units are more sensitive to these forecast errors, which units have the better forecast. So we can have at a glance a very complete information with a formulation that is relatively simple. So just to conclude, we have outlined, sorry that I couldn't go into details about this. We have outlined an approach to account for uncertainties that characterize DVPPs participating in different markets based on the robust optimization, which is trying to optimize, again, the worst case realization of the uncertainty range, provided that we define this strategy that we want to follow, either pessimistic, optimistic, balanced, okay? So it gives the user a lot of freedom. It gives the user the flexibility to choose which strategy to follow, parameter by parameter. So it can define a robustness budget for each uncertainty. we have also compared this with other solutions. We have seen that it also provides improved results from the feasibility point of view. And also we have found that it's extremely efficient and extremely computational efficient. So to solve the problem that we have seen before in the Spanish case, it takes less than 5 seconds. So the user can actually run several cases for one snapshot, for one market session, and define which strategy works the best for him in very, very little time. And with this, I pass the microphone to my colleague Enoch, which will give you the last part of the presentation on the real-time operation of DVPPs.
So I welcome everyone to the last part of the presentation, and I will be briefly discussing optimal real-time operation of dynamic virtual power plants under uncertainties. So I want to enjoin you to keep in mind everything that has been discussed previously by my two colleagues, by Lukas and Álvaro, and because this is just an extension of the discussion. So here we're getting into real time, and the questions we're trying to answer is this: how do we actually guarantee service evacuation? That is to say, we've gone to the market, offers have been cleared. How do we make sure that what we already promised, we're actually going to be able to deliver? And another interesting question we want to answer is this: how do we ensure service provision under limited flexibility? We generally do not have access to conventional power plants, which can do the easy ramping up and ramping down. And because we're also going into the world of dynamics, how do we actually ensure that we follow what has already been offered? And lastly, I would also like to point out how the location of DVPP assets in the network impact service provision. That is to say, when we have a couple of units, just like the image that Lukas showed, we have a group of fishes. They are not always going to be located on one particular node. So how do we ensure that we use good solution algorithms to make sure we get optimal solution? And lastly, how do we actually verify the applicability of what we have proposed? So this is the system that we have. It contains two major things. We have the system, which is this part, that is the DVPP, the dynamic model. And also we have the real-time operation controller. That is what determines the redispatch of our DVPP asset. And the out of the RTO framework is actually the redispatch algorithm. So we have a couple of inputs, which are the market clearance that has been discussed already. We have the state of the units, the line conditions, and of course, some of the disturbances that can happen in real time. And then the major output that we have is the active or reactive power set point of the DVPP unit. I'm going to go into some of these applications in a couple of slides. But I also want to show you the second part of this slide on the right. You can see, if you're familiar with Opal, this is actually how it's distributed. We have the computation subsystem and the console subsystem. So the console subsystem is essentially a graphical user interface where the user can actually interact with the real-time operation framework. And this is more like, if you picture it, a system operator sitting in a control room, or a DVPP manager sitting in a control room where you have the console, where you have a graphical user interface, and then the computation can actually mirror the field where your units are. So you generally do not have easy access. And in actual fact, during the execution, the user doesn't have access to the computation subsystem. You are basically controlling it from the console. So how do we activate the tools? And of course, I'll give the applications in the next slide. Essentially, we're trying to respond to events, like has been mentioned before. Sometimes we have under generation due to loss of unit. For example, there might be a freak weather event where the wind turbine has to shut down. And of course, you also have stochastic resource changes. For example, like some cloud covering the solar PV units in our case. So these events can actually be responded to by the tool which we have developed. And also we have a continuous optimization where we actually monitor operations. The TSO command comes into this into play in this respect. In Spain, as has been said before, the TSO actually sends active power commands every 4 seconds. So how do we actually respond to this? The DVPP is monitoring it and is also trying to respond. Additionally, there are new unit operating set points. For example, you are moving from 1 hour to the next. How do we make sure that this is done efficiently without affecting service quality? So 2 things in terms of the application. So we try to look at this from 2 major worlds. We have the planning world and then the control world, because we're also delivering service in real time. So the first part, which actually looks like mirrors a planning world, is the guaranteeing of frequency containment reserve. And in other words, this could also be the primary frequency control. So for primary frequency control, we're basically talking about milliseconds in this case. It's a bit difficult to cram an optimization algorithm into milliseconds. So what we try to do is to guarantee to the system operator that we can deliver the ancillary service in terms of primary frequency control values, which we have offered, that we can deliver it at a time when it is requested. So this part of the RTO, the real-time operation framework, tries to minimize deviations from declared offers. So we're trying to re-optimize what we have actually submitted prior. And essentially, we're looking at some of the constraints here: power balance, the total generation, and the total quantity of services which we have offered. And lastly, we're also looking at a very important part, which is the line limits and the voltage constraints. And why are we doing this? If you recall the analogy of the fish, which I also alluded to, we're talking about units that are not necessarily located on the same node. So we have units like scattered across different buses in the network. So we need line limits. We need to take account voltage constraints. And here we're actually using an optimal power flow. And because we're trying to guarantee that we can provide this service, we are not limiting ourselves to just the active power flow alone. So we're also taking care of the reactive power flow, because we want to think about we're having a holistic view of the system. So in this case, we are using a form of the AC power flow, actually an approximated form. And I'm going to show us that, like, at the end of the result. We know the full AC is non-convex, and it's a very hard problem to solve. So we're basically making an approximation of the losses and trying to make it fit into our optimization problem. So for this planning phase, we're solving it minutes prior to delivery, just a couple of minutes. And then we go to the second part, which kind of mirrors control problem, and it's the automatic frequency restoration reserve. And here we are minimizing the cost of service provision. So what we try to do here is respond in real time, essentially, to the TSO command. And like the other constraints, which can also be mirrored in the other application which I discussed, we have the power balance, the models of the units. But essentially here we have to take care of the RAMs for the DVPP units. That is to say, how fast can we actually go up or down? We try to compare with a battery, where you can actually go from P max to P main within a couple of milliseconds. And so in this, we also have to make sure that our units actually are able to follow the ramp requirements. And the dynamic performance criterion here is one that is very, very important. So according to the grid code for the Spanish TSO, which we try to follow, and I think it actually follows other TSO grid code. So it says for the AFRR response, you have to respond as a first order system. That is, within 100 seconds, you should have delivered 63.2% of the set point, of the power set point. So to make our life easier, we try to do this. Okay, let's be conservative a little bit. And what we did was this: like at the end of 60 seconds after we receive a TSO command, we actually want to get to 60% of the new set point. So in a way, we are always ahead of the curve in a little way, such that if a unit goes out of line, we can easily compensate, and we can quickly compensate and not fall foul of penalties of the TSO. So quickly, I will run through some test cases and results. And here what we're trying to see is the response of the DVPP to external disturbances and the response of units to the dynamic performance criterion. So I'm using this simple test system. It was developed by one of the work packages in the Positive project. It's a 7-bus system which has 2 solar PV units and 1 wind farm. And also it includes 2 demands in the DVPP. If you see the demand in the bus 4 marked in blue, it's actually not part of the DVPP, but of course it's also part of the general system, and the external system is connected at bus 1. The wind farm is actually working in deloaded mode such that we can offer both up and down regulation. The solar PV1 also in this case, and the solar PV2 only has the up regulation offer. The demand 1 and demand 2 in this case, they do not have regulation offers because when we did the computation for the market analysis, we discovered it did not make sense to actually have regulation offers because it was expensive. And according to the table, the priority of regulation actually goes like from the wind farm down to the demand 2. So first, we're trying to assess the turnaround time. So like I said, this is a real-time problem that we have to solve like at the snap of a button. And here we're trying to also see how do we evaluate the dynamic performance criteria of the DVPP response. So in particular, we are responding to AFRR, that is the automatic frequency regulation reserve, because it has the tightest constraints, and it's the one that can show. We're trying to see the worst case scenario. We're trying to put the algorithm to the worst case scenario test so that we can see how it actually performs. So we have sequential commands from the TSO and of course the DVPP response. So here I'm just actually showing us the delta as it is. So the dashed lines are the TSO commands, and then the thick dark line is actually the electrical measurement. So here we're actually measuring the electrical measurements, not the results from the optimization algorithm. The electrical measurement from what the machines actually give out and the offers that were made previously. So if you see the latency, you see that there is a small delay between the TSO command and when the DVPP actually starts giving its response. So that latency is the time it takes for the DVPP, for the algorithm we have developed to get the TSO command to do the redispatch or the reoptimization to communicate the results back to the DVPP units, and then they start responding. So the time you see is actually the old turnaround time. And of course, because we used Opal, we can measure this and get like real values, real-time values. We can see the latency, we can see we model the communication links, and we can actually see that yes, this could work in real time. So the latency is actually less than 1.8 seconds in all the scenarios, in all the sequences that we considered. Secondly, we're also evaluating the dynamic performance criteria of the DVPP response. And here we're basically just taking the first one, that is the one at t is equal to 20 seconds. And we're trying to see how the DVPP does respond. So here I'm showing us the full values. Like we said, the DVPP is an agglomeration, so all the units are working together. The 100-second response, what the TSO actually requires or actually expects is this line, the faded one here. But what the DVPP does is the dashed line. And here we said, yes, we try to be conservative, but this actually helps us to be able to manage some other disturbances, and it does manage it very well. So the new set point changes actually correspond to 79% of the expected regulation after 100 seconds. So around this point, we are well above and well within what is expected. So this is the envelope where we are always allowed to operate. So this window, and yes, we can see that the DVPP is in. And on the right part, we see the priority for regulation provision. Here we actually model this such that it can respond to the new platform for coordination of balancing service provision in Europe, which is termed Picasso, where the cheapest unit provides regulation up to 100%, and then the second unit takes over. And we see that this is the case in this example. Finally, I'm going to quickly show you this graph showing the computational cost and scalability of the real-time operation tool. So like I mentioned, we are using an approximation of the AC power flow. And this is actually it. We're using the logarithm transform of the voltage magnitude, which basically approximates the full AC such that it can take care of the losses, can take care of active power flow and reactive power flow in the same vein. So for a DVPP, what we try to see is, okay, how big can actually a DVPP get? So we try to take a limit. So we're using standard systems. So these are standard IEEE systems, the 13 bus and the 34 bus. Also, we did that for the 123 bus. But we see that, yes, the DVPP might not be able to grow more than 34 buses. And of course, in this 34 bus system, we have like about 20 units and going up to 8 gigawatt, like overall. So for the approximate power flow, we see that we can always solve our problem below the requirement of the TSO. That is to say, for any sequential commands, the algorithm is always ready for the next one, like with some time to spare. For the DC power flow, of course, it solves faster, but it doesn't include losses, and you do not get a full view of the system. And for the full AC power flow, though the average time is about 4 seconds, it basically beats, we would not be able to solve to accuracy the system there. So quick remarks. I think I'll just jump to quick remarks for the whole project since we're out of time. So what we have tried to do is to present a unique blend of robust optimization for bidding and real-time optimal dispatch tool. And we've tried to bridge the gap between electricity market strategies and, of course, the real-time operation, the on-ground operation. We have also tried to include uncertainty and user-centric flexibility. So the user can actually set how optimistic or how balanced or how neutral or conservative they can choose to be. And in terms of feasibility and efficiency, both of the tools which you have developed, both the ones that include market operation and the one that includes real-time operation, they are computationally efficient and they are very, very useful for comprehensive analysis. You can do as many tests and as many simulations as you would want. And the real-world validation, like I said, we actually did practical tests using polarity with real-time communication between two different computers, mirroring what is done on the field and what is done in the control center. And then for real-world benefits, implementing our tools can actually drive efficient market participation and optimal use of renewable resources. We're trying to see, yes, system operators can actually use this, renewable energy producers, and even developers can use this, and finally, to end-time consumers. I hope I've not taken too much time, and if you have any questions, please, it would be very nice to take them now. Thank you very much.
Yeah, thank you very much, Enoch. Thank you very much. Thank you, Álvaro. Thank you, Lukas. Presenting to us all the advancements in the topic of the bidding and operation of the dynamic virtual power plants under uncertainties that have been introduced in the positive project. Now, the floor is open, so please pose your questions. Now the speakers, we will have like 5 minutes to have this kind of roundtable. And well, maybe I can start with one question from my side. Your algorithm has been based on on robust optimization to solve the problem. But why you decided to use exactly this method and not others like stochastic optimization?
Yeah, okay, I think this one is on me. Thank you, Mateo. So basically, we had the discussion at the beginning of the project because typically what we have found at that time in the research papers and in the literature is to have a kind of hybrid. And so people were using stochastic programming for the objective function and robust optimization in the constraints. However, after a few chats with our industrial colleagues from the project, we soon realized that that was not possible, because in the stochastic programming, you need to define several scenarios, so as a tree of scenarios. So for hour one, you have these possibilities of states of happening, and then for the next hour, each of these states can become into different ones, so it easily becomes a tree, with all these branches. And then we need to define the set of scenarios, which are not always easy to define, for every single market that you want to participate in it for each day. So you have day market, then secondary, then different intradays. And then when we were talking to these guys, to the industrial partners, and say, well, can you provide the input data, the information that we need to generate this scenario? And they, well, it's just not easy. It's very difficult. So then looking at the robust optimization, we found that it's more complicated from the mathematical point of view to implement it. Once it's implemented, it's extremely efficient, but writing the equations can be was a little bit difficult. But then once you have that, the only thing that you need is the distribution of the forecast that, of course, they can generate. And then you just need the median, minimum, and maximum deviations. You don't need to generate scenarios for every single market session. And also, if you want accuracy, then you need to generate more scenarios, which also increase the complexity of the problem, increase the number of variables, the computational burden. Whereas for the robust optimization, everything stays more or less contained in that regard. So there were many reasons for us to go for the robust optimization in this case.
Okay, thank you very much, Álvaro. The next question concerns, I think, the core maybe of the project, and it is, what is exactly the difference between virtual power plant and dynamic virtual power plant? Is it just excluding the energy storage system that generates this difference? And why have you decided to exclude the battery while it is a common resource that is used by other research activities?
Okay, that's a good question. I start answering it, and then my colleagues can jump in. So basically, the difference between the VPP and then the dynamic VPP is that within the project, so we have to go a step back out of this webinar and see the whole positive project. The idea is that within the positive project, we tackled several dynamic aspects of the VPPs. These aspects refer to local issues. So how do we have to control the VPP? So we go really into the control problems. How we do have to control them locally to achieve certain objectives. But it also extends to the global dynamics, means system-wide dynamics. So the question was, okay, we are able to control the VPPs. They will do what we expect them to do. But how does actually the system benefits of all this? Because the good question is, even from the economic side of view, we somehow show that, well, for the VPP, we can make money. But the question is, well, does the system benefit of all this? So from the dynamic aspect point of view, the project as a whole also looked at this part. So what are the contribution of DVPPs or of VPPs that are coordinated, that are controlled in a centralized way or in a distributed way? How do they affect the system security, after all, system stability? So we have already two dynamic aspects, local ones and global ones. So this is very important. That's why the D is in, because this project looked at this aspect. And then, well, we have also, let's say, it's in a minor degree, it's also present in this planning or short-term planning or real-time operation planning problem, where we try to consider that there are some dynamic aspects which should be considered, for instance, because we imposed, not we, but regulation imposes a certain dynamic performance criteria of participants in secondary markets. So that's why we added these dynamic virtual power plants. It's not much different from the VPPs because we are aggregating different assets. It's true, we are mixing generation assets and demand assets. We exclude the batteries. I will answer this later. In this regard, the aggregation concept is not new. The new part is that we include these dynamic aspects within the overall DVPP framework. So how it is controlled, how it needs to be operated, and so on and so forth, and how is the impact of that on power systems. So that's why we made this difference from dynamic virtual power plants and just normal virtual power plants. The other part of the question was about the battery. Well, let me add another thing. Just we didn't include it, but at least can mention it. We even actually tackled from an economic point of view the VPP impact at system level. We did this on island systems, and island systems are very sensitive, let's say, to active power disturbances, and these affect the frequency of the system. So it's a frequency stability problem. And actually, we tried somehow to show the benefit at system level, which is kind of complicated to show, that the system benefits, in that case, the islands of VPPs, after all, if we consider frequency stability problems at the system operation level. So even at an economic level, we showed actually this positive, see the title of the project is positive impact. Now to the battery. Why battery? Why not? Well, this has not actually much to do with if it's VPP or not. That's the story behind the project. It has to do that the European Commission, in the call, they explicitly wanted to exclude battery. And that's our interpretation of this explicit exclusion was that what we actually first want to do is to make use of the existing assets. So if we can combine them, coordinate their control and operation, maybe we get a benefit without doing nothing else than just coordinating them. So we want to do that first before adding new technologies in the system to spend more money on new assets. And that was the whole idea. So that you have this portfolio, can you do better with what you have? If so, please do it. If then it's still necessary to have some storage system, well, that's fair enough. So the idea is let's exclude it to see how far we can get. After that, we need kind of storage systems, whatever they are. But the European Commission wanted to exclude battery storage system. Of course, another argument, I mentioned it partially in the introduction, was the problem of the batteries is, well, the raw materials they need, and after all, their disposal afterwards. What are you doing with this after you use them? So this way, we also avoided an additional garbage, additional waste, or initial waste problem and recycling problem, because we make use of assets without investing in other ones. I hope I answered more or less the question. I'm not sure if my colleagues want to intervene or add anything on this.
No.
Yeah, thank you. Thank you for your answer. And well, it regards by I mean, I will combine two questions. One regards the uncertainty budget. How do you calculate it? And also for distribution system, is it reasonable to base the optimization on the median and standard deviation? I mean, the way that you explained it during the webinar.
Okay, so I think I got the first question. The second question we will come back to that later. So how the uncertainty budget is defined, it's something that we are currently working on at the moment. What we have done so far is to let that budget be freely chosen by the user. as I said, it's a decision based on experience and on how well or how much you trust the forecast of a particular uncertain parameter. So you can define different budgets for different uncertainties. So prices may have a different budget than the stochastic generation by a wind farm, for instance, or a solar thermal unit, for instance. So we observed using real data, and this is answering also partially answering some of the questions that I see on the chat. We have indeed used real data from the prices and energy production that are available from the website of the Spanish system operator. So basically, we got a long time series of data, and with that, we try to build some realistic forecasts for our distributions. And basically, we observe, for instance, that we can trust way more, so we can use lower budgets on solar PV plants or solar thermal plants and for wind farms. And also for prices, typically we can trust more prices in the day-ahead market than in the secondary reserve, for instance, the forecast, I mean. So with that, we kind of have an idea of what budget we need to use in order to have realistic, let's say, solutions that are satisfying us from the research point of view. Now, for from the real use point of view, we are trying to take advantage of the high computational efficiency of our optimization problem, where basically we have done sensitivity analysis, parametric analysis for very sequentially increasing that parameter and see how the objective function evolves and which units affects the most and which everything, how everything affects that. So that, you know, the user can have all the information and then decide, okay, I want this budget. But possibly this is not the best way to be used in real time, in real life. So what we are trying to do is to go a step further, and this is still a work in progress, where we let the user decide another thing. We let the user decide how far he wants to be or he decides to be from the maximum benefit that he can get if everything was ideal, if the forecasts were exact. So we can have that information because that would be the deterministic problem, and then you can say, well, I want to exclude 20% of the worst scenarios. I want to exclude 15%, 50% of the worst scenarios. So he needs to choose only one value instead of 15, 20 budgets, only one. And then, based on a probabilistic assessment, taking advantage again of this parametric analysis that we can do with virtually no effort, the algorithm will try to identify the budgets that you need in order to get that 15%, 50%, whatever you have decided of scenarios, of worst scenarios out of your objective function. So we are still working on that. Now, I don't recall the second question, so if you can recall it, Mateo.
Well, if it is reasonable, the assumption of the optimization to use a median and standard distribution deviation. I mean, if it is reasonable for distribution system dynamic.
I mean, it's, as I would say, that is, and this is a debate that it can be a little bit more an opinion, right? But I see it as reasonable as using, for instance, scenarios, probabilistic scenarios. You know, at the end, you are building up a forecast based on probabilistics. So one is a probabilistic density function, another one is a scenarios based on probabilistic, or the probability of things happening. But at the end of the day, we are representing mathematically something that could happen in the future. And with that, we have this tool, the PDF, the probabilistic density function, that gives us that information. Now, typically in robust optimization, this is another advancement that we have done in this project. Typically for robust optimization, to simplify things, they consider symmetric uncertainties. So they take the mean and the standard deviation. And we have demonstrated in one of the papers, and this is answering another of the comments that I see in the chat, we have observed that this is not accurate. We need to take into account the uncertainty, so the asymmetries in the uncertainty, because that affect quite sensibly the results. And with that, I would say that using these distributions with the median and the positive and the negative deviations, you put yourself again in the worst realization for that particular budget. And then the rationale behind the robust optimization is not by ours, it's something that Bersimas and another colleague did when they formulated for the first time the robust optimization applied to another problem. Basically, they say, well, I will optimize the worst realization of these conditions, and then hopefully whatever happens is going to be better than that because I'm putting myself already in the worst. Okay, so I would say that it's as reasonable as using the scenarios in this case, and for us it was much simpler to define the input data because otherwise it would have been extremely difficult to define scenarios for wind, for solar, for prices, different markets. It was our only solution really to be used. I mean, the goal is to build this tool so that operators, so that practitioners, so that researchers can use it efficiently. Okay, and that was our purpose, and I think we did achieve it. And answering this question that I was mentioning before, we have a paper that is being already under review with all this formulation, with all the rationales, with all the hypotheses explained, and with all the results. And also, I encourage people to go into the project website, the Positive website, because eventually we will be uploading the deliverables where we also have all the formulation and even more case studies with all the input data and everything uploaded because they will be public. Okay, they are still under review by the European Commission, at least ours, but they will be there. And so I encourage people to periodically check that website because they will be uploaded there.
Yes, okay. And with regards to this, I kindly ask you to provide me with all the links and but also to the documents and the papers, and we can include those references in the material. I mean that we will be sharing in the ISGAN website, but also in YouTube. We will have the recordings of the webinars in the description. You can find all the links to the relevant material.
Okay.
So, and I also think that we need to close the webinar because yeah, we are over time, but there are a lot of questions that still remain unsolved. So maybe we will have the answer to this question in a written form. So I will forward those questions to the speakers and they will try to answer them. And so you will find a recap of these answers you will receive it by email. So yeah, thank you very much to everybody to join to this webinar, and thank you to Lukas, Álvaro, and Enoch to present their advancement in research. So I leave them the floor now to say some words to close the webinar, if you wish. Lukas, Álvaro, Enoch.
Well, from my side, the only thing that I can say is thank you to you, Mateo, and all the ISGAN Academy for allowing us to present our work, and especially for all the audience, because of course they are the core of all this. So thank you very much.
And also from me, it's been an honor presenting my work to everyone, seeing the names, the participants, and everyone. I really want to say thank you so much, and it will be also nice to connect with you after the webinar. Our emails are there, and I would be happy to answer questions. Thank you.
I can just join my colleagues. Thanks a lot, Mateo, for setting this up. Thanks a lot for the audience being here and having patience with us. And if you have any questions, further questions, please contact us directly. We will be happy to answer any doubts and so on. Thanks a lot.